The next topic is going to be moving into modern atomic theory, what we think about the atoms now. We'll go through the history of it and then finish off with what we know. Okay, so we've got the Greek model, we've got the Dalton model, and from those two models, scientists started to wonder exactly what the atom was. And so determining what the atom was one of the most important scientific prizes to be found at this time. So we're talking 1800s, mostly the late 1800s, early 1900s. So the six most important scientists with this are going to be J.J. Thomson, Ernest Rutherford, Niels Bohr, Werner Heisenberg, Frederick Soddy, and James Chadwick. I'm only going to briefly talk about Niels Bohr and Werner Heisenberg because we're going to talk about them for an extended period of time when we get to chapter 6. Okay, so J.J. Thomson is the most influential person in possibly Western science, but definitely in English science. He is head of the Royal Society, which is Britain's most important scientific community. And there was a person that was part of the society, but also was a little strange. Science at that time was also a little bit of science fiction. And so the person who, his name was Crookes, William Crookes, and he created something called the cathode ray tube. He created it to talk to ghosts. So he created an incredibly important scientific device that turned into a phenomenally important media device. And he was using it to talk to ghosts. So at least he accomplished something, even if his goal wasn't quite attainable. So what Crookes created was a tube that was evacuated, meaning it had no substance inside of it. And then he put a piece of paper inside of it, and inside of that paper there was it was painted with a glow-in-the-dark paint. So I have this glass tube with a piece of paper with glow-in-the-dark paint on it, and that's it. And then to that they attach a battery. And then that battery is at a very high voltage, like more than 1,000 volts. The voltage that comes out of your wall socket is 110, 120. That will obviously kill you. And we're talking about something on the order of 10 times more voltage than that. So let me pull up a video. Here's a short video of a cathode ray tube. On this side over here, on the left-hand side, the electrons are going to be jumping from here to the other side. They don't know what they're looking at this time, but the interesting portion about this is when Crookes talked about and showed the other members of the society the tube, it gave Thomson an idea. So you can see this is a magnet that they're using, and so the magnet was pulling, and they flipped the magnet over, and now the magnet is pushing. So Thomson realizes the object must have a charge to it. And in this case, we classify it as a negative charge, but it has to be a charged particle. The idea that part of the atom is negative implies something else, that part of the atom is also positive. And so this is where Thomson comes up with this idea that there's more than one part to an atom. So Thomson decides that the atom must be composed of a positive section and a negative section. And he's English, and he comes up with this idea called the plum pudding model. So in his idea of what an atom is, we've got this object, and there's some positiveness. The atom is mostly this positive part, but then there are these negative things that he called corpuscles, which we end up calling electrons, that can come off. So he understands two really important things, that the atom is composed of a positive and a negative, and that the negative can come off. Those two things are still true today. This idea that the positive is a solid mass is incorrect, but the idea that there is a positiveness to it is important. His idea of the plum pudding model comes from this, which is an English dessert called plum pudding. The whitest stuff here is plums, and the inner part here, the specks, those are raisins. The first year I taught at the college, I had an English guy explain exactly how his grandmother made plum pudding traditionally. So after presents, and after Christmas dinner, which was usually eaten in the early afternoon, she would go into the kitchen and she would make up plum pudding. So plums, raisins, sugar, I don't know what else she put in it, regardless. And she mixes all that together, and then to it, she mixes in an entire bottle of rum. She mixes it all up. She puts a piece of cheesecloth over the top of it and then ties it off. And then she takes that container and she puts it in her attic. And then they eat that plum pudding next year for Christmas, on Christmas Eve. So it sits in her attic for an entire year. No refrigeration. The alcohol kills all the microbes in it, and the cheesecloth keeps flies and dust and other particles from adding new microbes to it. So not something I'm going to try, but there you go. If you want to, plum pudding. So this is his idea. He's eating plum pudding and he's thinking about, well, maybe this is what the atom looks like. Okay. I had said a little earlier that the cathode ray tube turned into an important media device. Well, it turned into the television. So as important as the book, I would say the television is. So what you end up doing is having this cathode ray tube. So the old televisions are called CRT TVs, and these were very heavy, and they had a very long back to them. So this is what you were looking at. This would be your screen, and then there'd be all of this apparatus in the back. So voltage, electrical plates and magnetic plates. And what they do is they direct electrons. The inside of the glass on the TV is coated with a substance that eventually would make colors. Initially, it was just black and white. And so when the electrons hit it, it would produce a particular color or a particular color of gray within the spectrum. And that would allow you to have images, because you'd shoot one spot and that would be a color, and you'd shoot the next spot and the next spot, and you have an entire line of spots. And then the machine would drop down to line 3 and it would shoot it again with these electrons. And then this happened, initially it happened, I think about 15 times a second. And then we got it up to 30 times a second and 60 times a second. And now you can get refresh rates of 240 times per second. So what that means is every single dot on a very high-end television will be refreshed 240 times per second. That's a lot. When you pause something that's shot in that kind of, with that kind of camera, there's no blurring, because the shot is taken. They're taking 250 photographs with that camera per second and then displaying it on this screen. So the number of dots across the top is measured by the pixel number. So initially, standard definition was 480, and then that got up to 720, then 1080. Then you just start doubling those things. And so it's the number of dots across. So if you have a lot of dots, then the fact that it's pixelated doesn't look pixelated because the dots are too close for you to see. So definitely the opposite of what Minecraft looks like. Okay, so we need to talk about Ernest Rutherford next. So again, I told you that Thomson was the most important scientist in England, and Rutherford came to him after reading his report on what he thought an atom was concerning the plum pudding model. And he said, you know, it's great, thanks for moving this forward, but I think there's something wrong with your theory. And so what you might think would happen, that the most important person in science in England is being told by someone he doesn't know that his theory is wrong, that he might toss him out. But actually, he sat and listened to Rutherford and said, I'm going to give you a space to work in, some people to work for you, and some money to do your experiments. It was completely collegial. It is what science should be. If we were all ants or bees, this is the way it would be. We wouldn't fight over recognition or money. We would just do everything that's in the best interests of the project, in this case, learning what the atom is. So what Rutherford uses is a new technology. So radiation has been around forever, and we kind of noticed it about now. And he decided to use it as a piece in the experiment. So what he does, let me pull this little video down here. Grab you, pull you down here, make you bigger, make you full size. This video is on the YouTube list. I'll add that other cathode ray tube to the video YouTube list as well. So inside of here is some uranium, a rock called pitchblende, which shoots out something called an alpha particle. And this is a block of lead, which blocks those particles. And then there's this screen thingy here. And what this is like the paper that's inside the crux tube. This is painted with that glow in the dark stuff. This is just a lens to make sure that you get all the alpha particles that come flying out of the radioactive nucleus to go through in the same general barrel. And this is a piece of gold. This piece of gold is gold foil. Gold can be pressed into something monumentally thin, tissue paper thin. You can see through it thin. This is how people would keep pieces of wood that have been sculpted around for generations or 1,000 years. They would have something sculpted, and then they would have somebody create these thin layers of gold, and they would put it over the top of the wood. And then that object is said to be gilded. And now the wood won't be attacked by the oxygen because the gold is protecting it, and gold doesn't react with oxygen under normal circumstances. So it protects the underlying. So this is a phenomenally thin piece of gold. So what ends up happening is you open up this little door here, and you allow these alpha particles to shoot through. And what you're seeing is most of the time they just hit right here. About 1 out of every 8,000 times they ricochet back. That was phenomenal, because remember, Thomson had said that the atom is basically like plum pudding. So if you had a Ziploc bag filled with pudding and you shot it with a handgun, you would expect the bullet to go straight on through. You would not expect the bullet to come back and hit you. And this is pretty much what Thomson or Rutherford said when he got this experiment, these results. It would be like shooting a cannon at a piece of tissue paper and having it come back. You're obviously not shooting at tissue paper, and so you're obviously not shooting at plum pudding here. So the reasoning behind this is what Rutherford comes up with the idea called the nuclear model of the atom. And we used that word earlier when we were talking about the nucleus, and that the protons and that the electrons are in, or sorry, the protons and the neutrons are in the nucleus. So this is a bad, not good enough for me. These nuclei, the nuclei should be much smaller than the size of the atom, like 10,000 times smaller, but I guess that would be too small. So we have these alpha particles shooting through, and you can see most of the time they just pass through because there's empty space between the atoms, but the atoms themselves are mostly empty space. Only every once in a while are these particles going to hit. So the reason the alpha particles are hitting and ricocheting is because the nucleus is positive, like Thomson had thought, that there was a positive section, and then the alpha particles are also positive. So when they run into each other, they repel each other instead of sticking to each other. The relative size of the atom to the nucleus is it's quite large. The atom is. So let me pull up another image. Open image in a new tab. Oh, that's not right. I'm not sure why it's doing that. How about if I just download the image? Whatever, I'll just pull this down. This is the University of Michigan football stadium. It's the largest stadium in the United States. It's called the Big House, and you can fit 111,000 people in here. Think about that for a second. 111,000. Those are just people in the stands. That's larger than the population of Beaverton or Eugene. So if, let's say this entire stadium is our atom, right here on the M in the middle, you put a BB, that's the nucleus, and it's still too big. So you can imagine that if everybody in the stands was throwing something at that BB in the middle and they were all blindfolded, the chances of them actually hitting that BB are very slim, like 8,000 to 1. And so that's our situation. We've got this atom and this tiny nucleus, and the nucleus is where the proton and the neutron are. And that's the proton and the neutron are basically all of the mass. So all of the stuff of an atom is this tiny speck of the nuclei in the center. The rest of the atom is just open space, in the same way that our solar system is mostly empty space. We have this huge sun in the middle, but relative to the size of the whole solar system, it's very small. Okay, so these are our ratios. So let's go back over here, talk a little bit more about this. And so again, this was really awesome that Rutherford was able to work with Thomson and come up with the idea that perpetuated, that moved the theory along what the atom was. And then this same kind of thing happened to Rutherford later on. Prout and Goldstein, along with Soddy, determined that nuclei wasn't just a chunk of positiveness. It was actually composed of individual positive particles that we ended up calling protons. And so they realized that we have this small, densely packed positive core of particles, and that ends up being our nucleus, which is surrounded by the electrons, which are negatively charged. And so if I have an atom, the number of the negatives and the number of positives are going to equal each other. A little image of that. Soddy was the one that pushed Rutherford into understanding that there was something else going on inside the nucleus. And James Chadwick was the person who came up with the idea that the neutron existed. So for a very long time, about 30 years, the existence of the neutron was unknown. I've got a positive part of the nucleus and I've got a negative part of the nucleus. Why do I need a particle that's not charged? Well, it turned out the reason was because if you've got, scroll here, if I've got a proton and another proton, these guys are both positively charged. They don't want to touch each other. So it would be nice if I could put something else like the neutron in there to be like a buffer. So the positives don't have to sit right on top of each other. There are these neutron things that get in between the positives. And so this right here, 2 protons and 2 neutrons, this is what regular helium is. Helium, in this case, would be called helium-4 because it's got 4 particles in the nucleus. James Chadwick was a person who discovered this, and he was super anal retentive, and he was the best person in the world at the time of making high accuracy scales. And because he was, mining companies would send him ore, and he would be able to tell them if it was worth it to mine there. If the ore that he was given was dense, then the dirt was dense, then they knew there was pretty sure there were probably precious metals in there. And if it wasn't very dense, then there probably weren't any precious metals. So what he had discovered was people who were sending him samples of gold from the Ural Mountains in Ukraine, and the people who were sending gold from the United States, like around Arkansas, those golds did not have the same mass. And it was often way many decimal places back, but it mattered. And so he realized that there was something weird going on. And it turns out that that weirdness is something called an isotope. So Soddy and Chadwick determined that this isotope thing is related to the existence of the neutron. Okay, let's see. So what else do we want to talk about? So in Dalton's second assumption about his atomic theory, he held that the identical atoms of the same element are identical in their size, mass, and properties. They are the same size, they are the same, have the same properties, but their masses are different. And this is what Soddy and Chadwick determined, that their masses could be different. Again, these final 2 scientists, Bohr and Heisenberg, we're not going to talk about them now. We're going to spend basically half a chapter talking about these guys. And so here's what our atom looks like. I have this space, empty space, that the electrons fly through. And then I have this nucleus. And you can see this is 10 to the negative 10th, and this is 10 to the negative 15th. So we're talking about 5 orders of magnitude difference between them. 100,000, 10,000 difference in their size. So the atom is 10,000 times smaller than the nucleus, which makes sense because they were shooting those particles through and they were getting about an 8,000 to 1 ratio of when they would ricochet off. So that number makes sense. And that's all I got for this section. So we've got the Greek model, the atom we started with the last set of notes, and then we're talking about Thomson's idea that the nucleus, sorry, that the atom is a positive and the negative can come off. And then we've got Ernest Rutherford coming in and saying, okay, but that positiveness turns out to be this solid, small, positive section that he called a nucleus. And then we've got Goldstein and Prout coming in and saying, okay, so this solid nuclei isn't actually solid. It's composed of different positive charges. And so the positives in the nucleus equal the negatives of the electrons in orbit, and that makes your atom. And then Soddy and Chadwick came up with the idea that there are neutrons and that atoms have different masses, even if they're the same type of atom, like gold. Two gold atoms can have different masses, or two carbon atoms can have different masses. And that's what we've got. All right.